Hello, everyone, and welcome to part 3 of derivatives of exponential and logarithmic functions. I'm actually starting with a little answer section here for this next set. If you would like to try and figure it out on your own, you can take a screenshot. All right, and I'm going to go back and actually do the problems out. So an interesting concept that we did last time was we had an ln in front of something, and we expanded it. So when we had this, we could switch it to ln of x plus 1 to the 1/3 minus ln of x minus 1 to the 1/3. And then we made it even simpler by bringing the 1/3 down. This was great. This is what we did last class. And then, of course, the derivative was super easy. But keep in mind, if there's not an ln there, you can't do that. And somebody thought to themselves, what if there was an ln there? Could I put an ln there? And so that's actually what we're going to do today. We're going to put an ln on both sides. We're going to take the natural log of both sides so that we can use this fantastic property that allows us to simplify the problems. So on number 1, you see that x is stuck in the exponent. You can't do that. There's no exponent rule like there is for a product rule or a quotient rule. So I'm going to take the natural log of this side, because whatever you do to one side, you have to do the other, and the natural log of this side. And now I'm going to bring down that x, and now I can take the derivative. You've already learned implicit differentiation. So I'm going to write this as 1 over y, but then I have to do the derivative of y, which I'm going to call y prime. And then on the other side, you're going to have to use product rule. Don't forget that. So the second times the derivative of the first plus the first times the derivative of the second. That gives me y prime is equal to the natural log of x plus 1. And we do need to get the y prime all by itself. So I can multiply both sides by y. There are two ways. I'm just going to move this up here. So y prime is equal to y times ln of x plus 1, or sometimes so that it only has x's in the equation. Since y is x to the x, people will change it to this, but both answers are acceptable. So now we get to combine our knowledge of implicit differentiation, where we were taking the derivative of the y also, with product rule, with derivatives of logs, with simplification of logs. It is all coming together. Number 2, again, I can't deal with this problem with that tangent stuck as an exponent. And so to get rid of it, I'm going to take the natural log of both sides. That allows me to take the tangent and put it out in front using the rules of logs. Now I'm going to do implicit differentiation. The derivative of the natural log of y is 1 over y times y prime. And then on this side, again, product rule. The second times the derivative of the first plus the first times the derivative of the second. This doesn't really get much easier. I am going to multiply both sides by y, but I'm not sure that this simplifies to anything really great. Natural log of x, secant squared x. I guess I could write it as tangent of x over x. I'm not sure that that's necessarily better, just different. And there's my answer. So as you can see, these problems aren't ridiculously hard, but it is a new concept. This concept is, this operation is called logarithmic differentiation. and it is a really neat process. So on this one, it's really just that this one is complicated. You could do it using product rule and quotient rule in the same problem, but it would be pretty awful. So I'm going to show you how even if there's not an x in the exponent or a tangent of x in the exponent, this is still a great method. So using logarithmic differentiation, I'm going to take the log of both sides. And now that this is a log, I can expand it. So because things are being multiplied, I can change them to addition. And I'm going to just in my head already know that that's a 1/2 that's going to come out in front. Because this is division, I'm going to change it to subtraction. And again, at the same time, I'm just going to go ahead and bring that that 2/3 out in front. And now this is a really nice, easy derivative. No product rule, no quotient rule, just straight up logarithm differentiation, which is great. So the derivative of the natural log of x is just 1/x. This 1/2 I'm going to write horizontally instead of diagonally. Now this is my u. So the derivative of the natural log of u is 1/u times the derivative of u. Now I have a new u. Now this is my u for this little problem. So the derivative of the natural log of u is 1/u times the derivative of u. I can simplify this, not a ton, but enough to make it look tidy. 1/x. On this one, if it helps you, you could put this over 1, multiply straight across the top and straight across the bottom. And straight across the top on this one and straight across the bottom. If you leave that 3 times the quantity x plus 1, that's still correct. You can do that. Now I'm going to multiply both sides by y. And I'm going to clear that too. In order to clear these y's, and my final answer is y prime is equal to y times 1/x plus x over x squared plus 1 minus 2/3x plus 3. Sometimes I ask you guys to get a common denominator. I'm not really sure in this case it pays off, but you could if you wanted to. Next one. So this one does have an x in the exponent. That's a sure sign that you're going to need to do logarithmic differentiation. So I take the natural log of both sides. That allows me to simplify. So I'm going to bring that 1 over the natural log of x out in front, which just leaves me with the natural log of x. This simplifies quite nicely. These cancel, and I just get this. So interestingly, a lot of people get this very nice, lovely problem wrong at this point. They take the e of both sides. They're like, oh, I can get rid of the natural log with an e, and then y is equal to 0. You can do that if you want to, but don't forget to actually take the derivative. The goal isn't to solve for y. The goal is to get the derivative. So while this is not wrong, I'm going to stick with what we've been doing. So 1/y times y prime, and the derivative of 1 is 0. And then if you multiply both sides by y, you do still get y prime is equal to 0. You might have seen in the answer that it had little x's greater than 0. That's just because you can't take the log of a negative number. You're not required to write the domain unless I ask for it. Okay, here is another one that somebody might look at and say, wow, I'm going to have to use product rule and quotient rule and all kinds of awful things. But before we do anything, don't forget, I always want your first thought to be, can I simplify this? So absolutely, on this side, it's to the 5th power. So if I raise this to the 1/5 power, I think something good will happen. Let's see if we can make this work a little better. So inside here, this is x plus 1 to the, it's got a square root, so to the 5/2. And this is x plus 2 to the 10/2, because it's a square root. And I'm raising all of that to the 1/5. So now I get to multiply my exponents, x plus 1 to the 1/2, and this is just a 5. So x plus 2 to the 5th to the 1/5 is actually just x plus 2. So now you're really going to have to decide whether or not you think quotient rule, which is not that bad at this point, or logarithmic differentiation. Obviously, I'm going to do it by logarithmic differentiation because that's what I'm doing today. But you could do it by quotient rule. So y prime is equal to, oh, not yet. We have to take the log of both sides. I was going to do it by both ways, but I'll do it the second way. So the natural log of y is equal to the natural log of x plus 1 to the 1/2 over x plus 2, which means I can simplify that to 1/2 natural log of x plus 1 minus, because it's in the denominator, natural log of x plus 2. This becomes 1 over y prime is equal to 1 over 2, this is my u, 1 over u du, minus, now this is my u, 1 over u du. I realize a lot of you are not writing the 1. That's fine. And if I multiply both sides by y, that leaves me with y prime is equal to y times 1 over 2x plus 1 minus 1 over x plus 2. This is a perfectly valid answer. But if it wasn't the answer that you saw in the back of a book, say, or at the end of a worksheet, then it's your job to figure out if your answer matches the other one. So probably all they did was multiply this one on the top and the bottom by x plus 1 and by 2 to give it a common denominator, and multiply this one by the x plus 2 on the top and the bottom. And that would give you y prime is equal to y times, so now this numerator is going to be x plus 2 minus 2x minus 2. I'm distributing the negative and the 2 to the x plus 1 at the same time. Because we're in calculus, we have to be able to do a couple things in single steps. And then that gives me y prime is equal to y times, the 2's cancel, x minus 2x is minus x over 2 times x plus 1 times x plus 2. So learning how to get a common denominator could help get you an answer if it's in a multiple choice test that you recognize. If you want, you can skip ahead. If you need to see one more quotient rule, you might decide, let's see, how many steps was that? We took the log of both sides, we simplified it, and then we actually did the derivative. We ended up doing more steps, but let's say we stopped here, 1, 2, 3, 4. So let's just compare it, because I think you need to know what it is that you'd like to do. So now using quotient rule, this would be the bottom times, the bottom times the derivative of the top. Oh, I already don't like it. I'm getting a negative 1/2 minus the top times the derivative of the bottom all over the bottom squared. That gives me, now you have to factor out this negative 1/2. So x plus 1 to the negative 1/2 comes out, and that leaves me with 1/2 and x plus 2 minus, there's 1 x plus 1 left. I don't know about you, but I am not preferring this method. Some of you aren't even watching. Like, yeah, I skipped ahead a long time ago, Mrs. Shaffer. This is terrible. So this gives me 1/2 x plus 1 minus x minus 1 over x plus 2 squared. And now the x plus 1 to the negative 1/2 is on the bottom. And I have to multiply the top and the bottom by 2. Well, these cancel to clear the fraction. I have to do it on both sides. And that gives me x minus 2x over 2 times x plus 2 times x plus 1 to the 1/2. Whew. That was a lot. Now, here's my big point, though. The reason I did this is because I wanted you to see that the two answers look like they don't match. Right? So if you look at this and say, oh no, it doesn't even give you the same answer. It does. Remember, this one has a y in it. So if you replace that y with x plus 1 to the 1/2 times negative x over x plus 2 times 2 times x plus 1 times x plus 2, it does work. So here's your two x plus 2 squareds. This x plus 1 to the 1/2 and this x plus 1 would make an x plus 1 to the 1/2 on the bottom. There's your negative x and there's your 2. So they are the same. But again, if a book uses quotient rule and gets this answer, and you use logarithmic differentiation and get this answer, the chances of this answer being there with that y, very slim. So you need to know how to convert the two answers. Okay, last practice problem. So on this one, I don't think it's worth raising both sides to the 5/4 because it's just going to be ugly over there. So I'm going to show you how to do this one without doing that. I'm going to take the natural log of both sides. And now I'm going to simplify it. This becomes 4/5 natural log of y. And this becomes, okay, so I can separate that into 1/2 natural log of sine of x plus, because it's being multiplied by the cosine, another 1/2, they're both under the square root, natural log of cosine of x minus the natural log of, and I know it looks like there's something you should be able to do there, but there's really not. It's just minus the natural log of that entire denominator. Now we can actually take the derivative. That would become 4/5 times 1 over y times y prime is equal to 1/2. Now this is my u. So the derivative of the natural log of u is 1 over u times the derivative of u. Now this is my u. So I take the derivative 1 over u times the derivative of u. Now this is my u. U keeps changing. And it's going to be 1 over u times the derivative of u. The derivative of u is going to be 0 plus 2 times 1 over x. This is a huge problem. Y prime is equal to, so I'm going to multiply both sides by 5y over 4 to cancel with this. So I'm going to multiply this entire side by 5y over 4. I'm going to put it on this side. I don't know why, just always do. And this is going to be cotangent of x over 2 minus tangent of x over 2 minus 2 times x times 1 plus 2 ln of x. So how did I get that? Cosine over sine was cotangent. Sine over cosine was tangent. And on this one, this is straight across the top, 2 over x times 1 plus 2 ln of x. I think that the final answer might have multiplied out the 5/4. I think just because there's other numbers there, it worked out. But you can leave the y out in front. But if you multiplied this, you would get 5 cotangent of x over 8. I don't know that it's really any better. I just wanted you to know where the answer came from. 5 tangent of x over 8 minus, and then this time it would be 10 over 4, which would be 5 over 2x, 1 plus 2 ln of x. It's an awful problem, but it is still so much better than trying to use product rule and quotient rule with that, in my opinion. So keep logarithmic differentiation in mind as a way to tackle a really challenging problem. It did make it simpler, believe it or not. All right, we have 2 word problems. I'm always throwing in a couple word problems. This one is a little ironic, given our circumstances, but I have literally done this word problem for 15 years. So didn't just make it up for this year. The spread of the flu in a certain school is modeled by the equation P of t is equal to 100 over 1 plus e to the 3 minus t, where P of t is the total number of students infected t days after the flu was first noticed. Many of them may already be well again at time t. Estimate the initial number of students infected with the flu. So whenever you see initial, that always means t is equal to 0, means at the start. So for part A, P of 0 is equal to 100 over 1 plus e to the 3 minus 0, which is going to be P of 0 is equal to 100 over 1 plus e cubed. I cannot do that in my head. So I'm going to get out my calculator and I do 100 divided by 1 plus e. There is an e button on your calculator to the third. I get 4.74. This is talking about number of students, so approximately 5 students. That's part A, the initial number. So pretty much there was 5 students infected with the flu, and it's going to spread according to this model. I mean, not to be funny, but do you not think that they have models for corona right now? Absolutely. Okay. They're always reworking the models to try and figure out how fast it's spreading and what they expect to happen. They've also been wrong a lot, but that's besides the point. Part B. How fast will the flu be spreading? So this is a new concept that I need you to understand. We've talked several times about SVA, where this is the distance, this is the velocity, and this is the acceleration. And that's a great way to explain the relationship between derivatives of a function. However, it actually works for any amount. This is the rate at which the amount changes. So if you have a distance, Your velocity is the rate at which the distance changes. But if yours is people, if I take the derivative, I can give you the rate at which the number of people change. So when they say how fast, they want the derivative. So P prime of T is equal to quotient rule, the bottom times the derivative of the top, 0, minus the top times the derivative of the bottom. The derivative of E is E to the exact same thing times the derivative of the U, which is -1. That's a really easy thing to forget. All over the bottom squared. So P prime of T is equal to this -100 and this negative actually make it +100, e to the 3 minus t over 1 plus e to the 3 minus t squared. How fast is the flu spreading at 3 days? So this is a general formula. I can tell you on any day how fast the flu is spreading if this formula is correct. But I want to know it at 3 days. So at 3 days, oh good, they were so nice to me. 3 minus 3, that's something I can do without a calculator. E to the 3 minus 3 squared. So this is 0, and anything to the 0 power is 1. Again, anything to the 0 power is 1. So this is 100 over 2 squared, which is 4, which is 25. Now think about what the unit is. If it originally represents people, then this is going to be people per time. And what is the time? Days. So people per day. That's how fast the flu is spreading. For part C, they want to know when the flu spread at its maximum rate. So I hope it makes sense that in the beginning, the flu is not spreading very quickly, but then it's spreading more and more and more. And eventually it's going to go back down again, where not that many people are getting the flu anymore. So to find out what its maximum is, it's pretty easy. We're just going to graph it and then find the maximum. The key is you don't want to graph the original function p. P of t represents, remember, the number of people with the flu. So if you graphed that, then there would be, remember, it started out as approximately 5 people, and then more and more people got the flu, and then it clearly leveled off and nobody else was getting the flu. It maxed out. But what we want to know is a graph of the rate. So the rate is something that's going to go up. It's getting faster and faster and faster, and then the rates start going to decrease. And of course, you guys know a lot about this because of COVID right now. So we want to make a graph of the derivative, which doesn't seem that bad. You just think, yeah, we found the derivative. We're going to take this derivative and plug it into y1 and have our calculator find the max. But on the outside chance you didn't actually have to find the derivative, if you hadn't done this math yet, I'm going to show you a really cool way on your calculator to make your calculator graph the derivative without actually figuring out the derivative. Okay, you ready to see something really cool? So I tried to save a minute. I already typed the equation in. So this is my original equation. And you might be thinking, no, Mrs. Shaffer, we wanted to see a graph of the derivative. I know that. But I want to show you how you can make your calculator graph the derivative without actually finding the derivative. You can use the n-deriv button. So math 8 n-deriv, which means it's finding n stands for numerical. So it's going to find the numerical derivative of y1. Watch this. So I'm going to go to vars, y-vars, function y1. We are going to use that so often I can't even tell you. So you're going to want to learn that. It's vars, y-vars, y1. And then instead of saying I want to know the derivative at a certain number, I'm going to put in x. I want to know the derivative at every single number. So when I hit graph, it graphs the original function, and then it graphs the derivative. Ooh, and look, there's the derivative coming back down. So I can't see the whole graph. I need to change my window. Now try and remember that. We just need to start at time 0. And I don't know, that would mean the flu was over in 10 days. Is it over in 10 days? Actually, we could kind of see from the graph that it looked like it might have been, but let's change it to 15 just to be sure. And then remember that the Y stands for the number of people with the flu. So at first, there was only 5, but it's not going to be negative people. And let's just say, I don't know, 200 people get the flu. So when I hit graph, there's the people getting the flu. That means, so on the blue graph was Y1. So a few people have the flu. In fact, I can see I went way too far out. Let's just change it so we can blow it up a little bit better to 8 days. Okay, so there's the people getting the flu, and then it levels out. No more people are getting the flu. Everybody that's going to get it has it. But the second graph is the derivative. What does that mean? It means that it's the rate at which people are getting it. So more and more people are getting the flu, and then it kind of maxes out. Like it's at its biggest rate. And now less people each day are getting the flu until no new people are getting the flu. That's what the red graph means. And it makes sense because right here, look how fast the number of people getting the flu is growing. It's really going up. That's why it's at its maximum rate. So the blue graph is the original function, the number of people with the flu, and the red graph is the rate. And they wanted to know the maximum rate. So I want to maximize the red graph. How can you be sure to maximize the red one and not the blue one? Just by turning the blue one off. So I go over to the equal sign, I unhighlight it, I hit graph, and now I don't have to worry. So your calculator is literally doing the derivative for the first function over and over and over again. I hit second calc. I want to find the maximum. That is not the left bound. So I'm going to say it start at 0 and go over to 1, 2, 3, 4. By day 5, it's definitely there. I don't want to take a guess. So I hit enter, and there it is. The maximum is on day 3, 24.999, pretty much 25 people per day are getting the flu, which is what they asked us, how fast was in part B, how fast was the flu spreading at day 3. Turns out that was the maximum day. On day 3, that was the highest it ever was 25 people per day. So very, very cool stuff that your calculator does. Okay, last problem. So the question says let f of x be equal to 2 to the x, and it wants f prime at 0. So I know you've just learned this, so you don't have it memorized. If you have y is equal to a to the x, then the derivative is again a to the x, but you do have to multiply by the natural log of a, and if it was a u, then you'd also multiply by du. So f prime of x is equal to 2 to the x times the natural log of 2. So f prime at 0 is equal to 2 to the 0 times the natural log of 2, which is 1 times the natural log of 2, natural log of 2. Use the definition of the derivative to write f prime of 0 as a limit. You are going to have to know this. The limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x. This is the definition of the derivative. So I know it seemed like you were mostly just working on the math when we learned it, but now you just need to understand it as a concept that a derivative is the slope at a point. But since we always need 2 points to find slope, the limit is our tricky way of getting the derivative at the slope at a single point, and we call that the derivative. So f prime of 0 is equal to the limit as h approaches 0 of f of 0 plus h minus f of 0 all over 0 plus h minus 0. So this simplifies to f of h. And what is f of h? 2 to the h. What is f of 0? Well, anything to the 0 power is 1. So I got that from doing 2 to the 0, which is 1. And of course, the 0 and 0 cancel, and we get h. So this is equal to this. So now it says deduce the exact value of this limit. That's what we did up here. Remember, we already found f prime of 0. Using the rules of derivatives, we found out that it's equal to the natural log of 2, which means this limit is equal to the natural log of 2. So if you're in AP, it's very possible that they won't guide you through. They're not going to give you step A, they're not going to give you step B. They're going to jump straight to part C and see if you can figure out that the answer is the natural log of 2. So this is a huge and important question. And of course, if you just take it one step further, then what is the value as h approaches 0 of 7 to the h minus 1 over h? Natural log of 7. All right, that's it for our third video on derivatives of exponential and logarithmic functions. Great job.